Today we will discuss about the concept of torque. Have you ever given it a thought that why are doorknobs always attached towards the extreme end, far away from the hinged end? Or why are the handlebars of wrenches made large? Now that you have started thinking, the obvious answer that you come across it that it becomes easier to rotate them, but why it is so? The answer is torque. তো একটা ডোর রোটেট করছে আর একটা রেঞ্চ রোটেট করাচ্ছি, তার জন্য মেন ফ্যাক্টর যেটা রেসপন্সিবল, দ্যাট ইজ নোন অ্যাজ টর্ক. Torque of an applied force represent the rotational capability of the applied force to rotate the line joining the point of application of the applied force and the axis of rotation. Let's see an example. Suppose here is a point or here is an object which is situated at a distance of r vector from the origin, and let F is the applied force on the object which is acting at an angle of theta, suppose. Now, is this F vector capable of changing the orientation of R vector? That is, it is capable of changing it by an angle of phi. To understand this, let's break the F vector into two components. Here the component is F cos theta, this is F parallel, and here the component is F sin theta, this is F perpendicular. Here the component F parallel, that is F cos theta, clearly cannot change the orientation, it changes the distance r. But the component F perpendicular clearly can change the orientation. Hence, we should try to maximize its value. Therefore, keep in mind that whenever we talk of orientation capability of F vector, we think of F perpendicular. It is also observed that if we fix F vector and only change the point of application, increasing R increases rotation capability and decreasing R decreases the rotation capability. Hence, the rotation capability of F vector, that is the torque of F vector with respect to the origin, tau equals to R into F perpendicular, that is R F sin theta, or R sin theta into F, that is R perpendicular into F, where R perpendicular can be seen as the component of position vector which is perpendicular to the applied force. Let's draw its diagram. Here is the object situated at a distance of r vector. Here is F vector acting at an angle of theta. Therefore, this angle also equals to theta. This is r sine theta, that is r perpendicular, and this is r cos theta, that is r parallel, and this is tau vector. So the rotation will also have a direction, either clockwise or anti-clockwise, with respect to an observer. Now, for example, in the above example, the torque is anti-clockwise. In vector representation, we can find it by using the right hand curl rule, where we curl the fingers of the right hand in the sense of rotation, keeping the thumb straight as shown in the figure, and the direction in which thumb points give us the direction of axis of rotation. This is our axis of rotation. Let the plane of paper be the xy plane. Hence, we use the following convention to represent clockwise and anti-clockwise rotation. Number one, clockwise, this is or this or minus k cap, and number two, anti-clockwise, this is or k cap. So in vector form, torque of the applied force is tau vector equals to r cross f. Remember that torque of a force is axis or point of the observation dependent, since r vector is the position vector of the point with respect to the origin, which was our point of observation. Hence, changing it means changing tau vector. So, when can the torque of a force be zero? Torque of a force be zero in two cases. When the applied force passes through the point of observation, then r cross f that equals to 0. When the applied force passes through the point of observation. And second case, applied force is parallel to axis of rotation. As example, suppose it axis of rotation for a door. This is a door. Here the weight of the door is mg. The door is hinged at one of its slides, which behaves as axis of rotation, and the weight mg tends to turn the axis of rotation itself, which is fixed. Hence, mg will not create any torque here. Now, next move to angular momentum. Angular momentum, angular momentum, which is denoted by L, it is a measure of the amount of rotational motion of an object with respect to an observation point in the same way as linear momentum is seen about the as the amount of translational motion in the object. It is measured in three different ways depending upon the type of motion. In case of pure translational motion, in case of pure translational motion, L vector equals to R cross P, that is R cross MV, that is M into R vector cross V vector. Here r vector is the position vector of the center of mass with respect to the point of observation. Now let's draw a diagram. Suppose here is the object, this is the center of mass, which is situated at a distance of r, and let this is a v acting at an angle of theta. So along this the component is v cos theta, that is v parallel. Along this the component is v sine theta, that is v perpendicular. This angle is also theta. Here draw a perpendicular. This is r sine theta. So with respect to the origin, L equals to mvr sine theta, or m into v sine theta into r, or m into v into r sine theta. That means either m into v perpendicular into r or mv into r perpendicular. So this is angular momentum in case of pure translational motion. Now next move to pure rotational motion. Second case, pure rotational motion. Pure rotational motion. In case of pure rotational motion, suppose here is the body, rotates with angular velocity omega. Here is a small elementary mass, suppose dm, situated at a distance of r. So here v equals to r omega. In case of pure rotational motion, the velocity of an elemental mass dm, v equals to r omega. Now with respect to this axis of rotation, dl about axis of rotation, that equals to dm into omega r into r. That means dm into r square into omega. So angular momentum about axis of rotation, that equals to integration of dl, that is integration of dm r square into omega, that is moment of inertia about axis of rotation into omega, where I of AOR, that is represent the moment of inertia about the chosen axis of rotation. Now third case, that is translational plus rotational. Third case, that is translational plus rotational. Now here consider a diagram. This is the body, this is the center of mass. This is r vector or r of center of mass. Rotates about an angular velocity omega, and this is velocity of center of mass. This angle is suppose theta. Now with respect to the origin, here L vector that equals to R of center of mass into mv of center of mass plus I of center of mass into omega vector. This is the angular momentum in case of translational plus rotational motion. Now, the relationship between torque and angular momentum is like that L vector equals to R cross P, that means dl dt that equals to R vector cross dp dt plus p vector into dr dt, that is R cross F, because dp dt equals to F, plus V cross P. As V vector is parallel to P vector, therefore this equals to R cross F, and R cross F means tau. So tau equals to dl dt. This is the relationship between torque and angular momentum. Now, for an object rotating about this axis, angular momentum about axis of rotation that equals to moment of inertia about axis of rotation into omega vector. So dl dt that equals to moment of inertia is constant into d omega dt, that equals to I of a over into alpha. This is dl dt. So tau equals to dl dt, and tau also equals to I into alpha. Tau equals to dl dt, tau also equals to I into alpha.